Right. So, we will now move into a completely new topic. I think we have done a lot of search. Now, we will move into a chapter on knowledge based systems, logic and deduction. So, this is a new thing which we will start working at from this thing, and we will see that it is a combination of search and deduction which will make up for almost the majority of the different kinds of activities or computational requirements that we have in AI. So, in this we are going to study a bunch of different techniques for representing problems in logic and also techniques for deducing new facts and new rules from the existing ones. So, the important things are representation of real world scenarios and reasoning with logic. We will study firstly, to start with, a logic called propositional logic. Then we will see add further things into the propositional logic, namely quantifiers, to get into first order logic. Then we will study inference mechanisms in propositional logic as well as in first order logic, and we will see that depending on the expressibility of your logic, the cost that we have to pay is in terms of the computational complexity of reasoning in those logics. So, for example, while finding out the satisfiability of a propositional logic formula will be shown to be NP complete, the question of the satisfiability in first order logic or the validity of a formula in first order logic will be semi decidable. So, there will be cases where the problem will be unsolvable, like you have studied the halting problem of Turing machine. That was one of the problems that you came across which is unsolvable, right. So, we will see that inference in first order logic is also semi decidable, in the sense that in one direction we can say yes, but the other direction, the no answer, can be undecidable, right. So, we will look into those things. We will study some classical techniques called generalized modus ponens for reasoning in first order logic. We will study some kind of forward and backward chaining mechanisms for inferencing. These are popularly used in all the deduction systems, and we will also study a technique called resolution and give you an overview of logical reasoning systems that are currently used in practice. So, we will start with an example. We will start with a very well known classical example called the Wampus world environment. So, in that environment we have the following kind of thing. We have a grid representing a very dark cave. This cave has many chambers, and in some of these chambers we have pits. Pits, if you fall into a pit, then that is the end of you, right. So, these are very dark. So, you cannot see from outside the chamber whether the chamber has a pit or not, right. But you do have some information about the position of the pits, in the sense that you sense a breeze when you are in a pit, when you are in a chamber which is adjacent to a pit. So, for example, we have a pit here. So, you can sense some breeze here and some breeze here, right. You have a pit here and you have some breeze in these. Diagonally adjacent ones are not adjacent. By adjacent we just mean the ones which share a common wall with the other chamber. Now, these chambers also have walls. So, it is not the case that you can move from any one of those chambers to any one of them. There could be walls on some of them. For example, if there is a wall like this, then if you are in this chamber you cannot walk directly into this chamber, right. Also, in somewhere in this cave there is a wampus, some kind of nasty creature, and if you are in the same chamber as the wampus, then the wampus lives and you do not. The wampus can be on any of these chambers, it can also be on a chamber which has a pit, because the wampus is so large that it does not fall into the pit, right. In addition, the wampus has a stench. So, if you are in any of the squares which is adjacent to the wampus, you will get a stench, and you will also get a stench in the chamber in which the wampus exists. But if you have already entered that chamber, then there is no point actually getting or not getting that stench. And all of these stench, breeze, etc., can be sensed only when you are in the chamber where you have the stench or where you have the breeze, right. Now, the only reason for ours being in this horrible cave is that there is gold somewhere inside it, right, and the objective is to find the gold without falling into a pit and without being consumed by the wampus. Fortunately, in this initial formulation, the wampus does not move around, it does not change chambers. So, wherever it is going to remain there throughout the game. And we have some armory also. We have one arrow, and we can shoot that arrow along a straight line, say either this way or this way, not diagonally, we can shoot it along a straight line, and if there is no wall that is blocking it, and if you find the wampus in line of in the direction of in which you are shooting the arrow, then the wampus will get killed, and you will know that it has got killed because it will emit a terrible scream, right. So, you will know that it has got killed, right. So, this is the wampus world, and our objective is to find out a mechanism of getting the gold. You can shoot the wampus, you can go from one cave to one chamber to another, and you cannot see the walls. So, if you bump into a wall, you will feel a bump. So, you can backtrack and try some other path. So, as you can see, it is also a kind of search that we want to do, but except there is some inferencing that you have to do. If you just blindly search, then you will fall into a pit or you will go into a chamber which has a wampus. So, as you are searching, as you are moving from chamber to chamber, your knowledge is growing. So, you will be able to deduce that okay, in this chamber I have a breeze, so in some neighboring chamber there is a pit. So, say at this point of time it senses a breeze here. Now, here is a problem, it knows that one of these adjacent ones has a pit, but it does not know which one. So, for this particular kind of example, there is no foolproof way of finding the gold, right, because it has to take one risk at least, and if it takes the wrong move, that is the end of it, right. So, in many cases the wampus world is very unfair, but there are also certain configurations where as you move from square to square, you will build up your knowledge and you will start deducing that no, I found breeze there and I found a stench there. So, the wampus could be in that square, but not in this square. So, it is safe to move from this square to that square, right. So, these are the deductions that will come up. So, we will have to see how we can formulate all these criterion and all these possible information that we have just now told in form of a logic, right, and how we can use deduction to enhance our knowledge and eventually deduce a mechanism of finding the gold. We will come back to this example later. So, this is just what I told you just now, that adjacent means left, right, top or bottom, and then we have discussed what is a stench, what is a breeze. There can be one wampus, one gold and many pits. Agent starts from the bottom left square of the grid. So, again I have already mentioned all this. The agent dies if it enters a square containing a pit or the wampus. The agent can shoot the wampus along a straight line, but it has only one arrow. So, let us come to logic. What is logic? It is a formal system for describing states of affairs, and typically a logic will consist of two things. One is the syntax, which describes how to write sentences in this logic, and the semantics which tells us what those sentences will actually mean. And then we will have a proof theory for the logic, which will be a set of rules which will deduce, which will help us in deducing a set of sentences from another set of sentences, right. So, we will study some proof theories. If you have an improper definition of logic or an incorrect proof theory, then you can actually have all kinds of absurd reasoning. So, for example, if you say that if you say that A is a cook, right. Okay, so this is, there is this thing about this thing that in Bengali, Thakur means a chef. So, if somebody says that Rabindranath Thakur was a Thakur and Thakur means a chef, so Rabindranath Thakur was a chef, that is the kind of reasoning which can give you very absurd results. So, there you have to actually make a difference between the domains of what a Thakur can be and what a chef can be. There is an intersection, but it is not that one implies the other, right. So, we will see that for every logic there can be certain paradoxes, and then we will see that how we can get around those paradoxes, if at all. We will study several different types of logic, and these logics are characterized in terms of what exists and what is the belief of the agent. So, in propositional logic we will have facts, and the agent either knows that the fact is true, either it knows that it is false. So, a proposition can be true, false or unknown. In first order logic there can be facts, objects and relations. Again we have true, false or unknown. In temporal logic we have the notion of time. So, in addition to what we have in first order logic, we will have a special attribute called time. Again we will have true, false or unknown. In probability theory we will have facts, but we will have an associated probability with those facts. So, we will have degree of belief. So, what is the probability that this proposition is true, what is the probability that this proposition is false. And then we have fuzzy logic, where we have degree of truth, right, and the degree of belief is again between something between 0 and 1. Now, there is a difference between probabilistic reasoning, probabilistic logic and fuzzy logic. When we are saying that what is the probability that our new manager will be fat, so that is a probability, that we do not know whether that person is fat or not, right. We just trying to associate some probability based on the age of that person and other criteria. But in fuzzy logic we will, it is not a question of whether that person is fat or not, it is the question of how fat, right. So, it is the degree of the fatness that we are talking about. See, there is a difference between the probability of a person being fat and the extent to which that person is fat. So, in fuzzy logic we will deal with that kind of thing. We will say that okay, this person is tall, how tall? So, tall is not just a Boolean, it has a gradation, right. Whereas, in propositional logic and with logic where we will deal with Bayesian probabilities, we will talk about scenarios where we do not know about the value of the proposition and associate a probability of it being true or false. So, it is the probability of being true and the probability of being false, whereas in fuzzy logic it is how true and how false. So, this is our first look at propositional logic. So, I will first define the syntax and then we will work out several examples to get the hang of the thing. So, what we will have is a collection of sentences. A sentence can be of two types. It can be an atom, where an atom is either true or false, or a member of the set of atomic propositions. The set of atomic propositions are the basic propositions that will be true or false in our logic, right. Like for example, if we are talking about a person has passed or failed, right. So, passed is a Boolean. So, passed yes or passed no, right. So, that is a member of the set of atomic propositions, right. Then we will have sentences which can be atoms like this, and we can also have complex sentences. Complex sentences can be sentences connected together with connectives, where connectives can be and or, both wise implication, one side implication, right. So, if I say A implies B, it means if A then B. Whenever A is true, B has to be true, right. Whenever A is false, the sentence A implies B is vacuously true, right. And both ways connective means if and only if, right. And we have the negation also. So, you have complex sentence can be the negation of another sentence, right. Okay. Before we go into modus ponens, just let us look at one thing here, that when we are talking about A implies B, can you represent this in terms of the basic Boolean operators? This is equivalent to not A or B. Now, please try to understand the equivalence between these two, right. This is true when either A is false or A is true and B is true, right. And what does this say? Either A is false or B is true, right. In addition, if A is true, see if A is false, then this part makes it true, right. But if A is true, then we have to depend on this. So, it is B is true. So, if you just construct a truth table of these two sides, you will see that these two are equivalent, right. And how do we represent this? XNOR, A is XNOR of B. So, in other words, it is basically writing implication on both sides, that not A or B and not B or A, right. That is going to give you the XNOR of the two. Also, you can write the implication in another form. See, this is the same as writing not B implies not A, right, because so this says if A then B, right. So, if it is B, it must be the case that it is not A. If it is not B, then it must be the case that it is not A, because if it is not B and it is still A, then it will refute this, right. So, these are all equivalent things. So, this is just these are the some of the things which will help us later on in deducing different kinds of things. Now, let us look at the basic inference rules that we have in propositional logic. We will then use these to consider some examples of deduction. The first one, this is how we write an inference rule. As I was saying that in a logic you have the sentences, you have the syntax, semantics, and you also have certain inference rules which tells you how to deduce new things from the existing ones. So, on in the what we write above this line is the premises, and what we write below the line is what we can infer from that. Okay. So, if we have if we have alpha implies beta and we also have alpha, then we can deduce beta from that, right. So, alpha implies beta is a rule and alpha is a fact that is given to us, then we can deduce beta. Unit resolution rule is, if you have alpha or beta and you are given not beta, then you can deduce alpha. Actually, this is written as A, please read this as alpha, this is a mistake. So, you deduce alpha. Now, this and this are actually, you can think of them as similar, because when you have alpha or beta, you can write this actually as not beta implies alpha, right. So, if you have not beta implies alpha and not beta, then you can use modus ponens and actually arrive at alpha, right. So, it is the same thing, but these are different rules which have come up through reasoning. These rules are really old. These rules have come from the time when initial logic and deduction was proposed at the time of Aristotle, right. So, as you can see, modus ponens does seem like a Latin word, right, or a Greek this thing. So, these are really old ones. Okay. When you have resolution, you have alpha or beta and not beta or gamma, then from that you can deduce alpha or gamma.
So, given alpha means alpha is true.
Yes. So, given that either alpha or beta has to be true, and also given that either gamma or not beta is always true, we can deduce that alpha or gamma is true. How? See, either beta is true or not beta is true, right. Okay. Either beta is true or not beta is true. If not beta is true, then beta is false, so alpha has to be true. On the other hand, if beta is true, then not beta is false, so gamma has to be true. So, in both of these cases, either alpha has to be true or gamma has to be true, right. And this deduction is actually easy. What you do is, you take this premise and this premise, take their AND, right, and then you use Boolean algebra and you will eliminate beta and not beta and get alpha or gamma, right. If you take alpha or beta and not beta or gamma, then if you minimize it, you will get alpha or gamma, right? Beta will get eliminated. And this you can write also in implication form, where you write for alpha or beta, you write not alpha implies beta, and for not beta or gamma you write beta implies gamma. So, that is the same by using modus ponens, you can actually use transitivity here to obtain not alpha implies gamma, right. And not alpha implies gamma is the same as alpha or gamma, right. Okay. And there are many other rules which we will discover as we go further into deduction. So, let us take an example on deduction. So, here is one example that we will consider. So, these are the basic premises that are given to us. So, we are given that if the unicorn is mythical, then it is immortal, but if it is not mythical, then it is a mortal mammal, right. If the unicorn is either immortal or a mammal, then it is horned. The unicorn is magical if it is horned. So, these are all the premises that are given to us, and then can we prove that the unicorn is mythical, can we prove that it is magical, and can we prove that it is haunt. So, the question is that these three sentences that has been given to us, from that we want to deduce whether the unicorn is mythical, magical or haunt, right. So, we will formulate this in propositional logic and show how we can deduce whether it is mythical, magical or haunt, right. Okay. Now, the first thing that we are going to do is we are going to represent each of these as propositions. So, what are the set of propositions that we have? We will come back to this slide. We will come back to this slide. Let us look at the basic propositions that we have. The propositions that we have are the following. We will say umyth is unicorn is mythical, umort unicorn is mortal, umam unicorn is mammal, then likewise umag and uhorn, right. So, these are the 5 different propositions around which we will build our logic. So, now let us go back to each of those lines. So, let us start with the first one. If the unicorn is mythical, then it is immortal. So, we will write that as follows. If the unicorn is mythical, so umyth implies then it is immortal. So, it is not mortal. So, umyth implies not umort, right. So, this says that if the unicorn is mythical, then it is immortal. The second one says that if the unicorn is not mythical, then it is a mortal and it is a mammal. Clear? So, these two together is the first one. Slides please. These two together gives us the first thing, that if the unicorn is mythical, then it is immortal, if it is not mythical, then it is a mortal mammal. Then when we look at the second one, it says that if the unicorn is either immortal or a mammal, then it is haunt. So, let us come here and see if it is a mammal and it is immortal, or it is immortal. If it is either immortal or it is a mammal, then it is haunt. And the final statement says that if it is haunt, then it is magical. So, uhorn implies umag, right. So, this is the formulation of the set of sentences that we had written down in propositional logic, right. So, the key thing here is first choosing the set of atomic propositions, and secondly writing them down in terms of propositional logic formulas. Then what we do here is we deduce new things from here, right. Now, let us see what we can deduce from here. So, let us look at this one first. So, what we get here is from 1 and 2 we find that if it is mythical, then it is immortal, if it is not mythical, then it is mortal mammal. Now, one of these is always going to be true, right. So, I can say that always either this or this will be true. So, either this is going to be true or this is going to be true, right. So, here we can write from these two that it is either immortal or it is a mortal mammal, right. This is where we use resolution. Then when you look at this 5 and if you look at 3, then what we have here that this is this says that if it is a mammal and immortal, then it is haunt. Now, look at this thing, this says that it is either immortal or it is a mammal. So, this actually also implies that it is either u mod or u mem? Yes or no, right. So, because we have this and we have this, so we can deduce u horn, right. So, we have u horn, we have deduced u horn. So, we have deduced that the unicorn is horned, and then if you apply this one, then now that we know that it is horned always, we can say that it is magical. So, we have deduced that the unicorn is magical. So, we have been able to deduce that the unicorn is horned, and we have been able to deduce that the unicorn is magical, but we have not been able to deduce whether the unicorn is mythical or not. And as it turns out that in this case you will not be able to deduce whether the unicorn is mythical. Now, this analysis that we have done has been done in a somewhat ad hoc manner. So, we have to bring some formalism into the procedure. Now, if you look at this, that each of these sentences that we wrote is a Boolean formula. It is nothing but a Boolean formula over a set of Boolean variables. Each of these propositions is a Boolean variables, right. So, what we are trying to find out is, if you are given a set of Boolean formulas f1 and f2 and fk, these are the Boolean formulas that are given to us, and of two Boolean formulas is yet another Boolean formula. So, this is one big Boolean formula, and we are trying to deduce whether the goal is implied by this. So, we are trying to deduce that if all these Boolean formulas are given to us, and we are told that these Boolean formulas are all true, they are all valid formulas, then can we deduce the goal, which is another Boolean formula, from this? Can we deduce the goal from this? Can we show that this is true? So, we are trying to see whether this is valid, right. Now, we will reduce this to the Boolean satisfiability problem. And how are we going to reduce this to the Boolean satisfiability problem? So, if this is valid, if this whole thing has to be valid, then the negation of this has to be, it has to be unsatisfiable, right. The negation of that has to be unsatisfiable. Now, what is valid? It means that no matter what values you assign to these Boolean variables, you will always get true. A valid formula is one where whatever values you assign to the Boolean variables, this formula will evaluate to true. Satisfiable means that there exists some assignment to the Boolean variables which makes this formula true. So, there is a difference between satisfiability and validity. Here we are interested in deduction. So, we want to know whether always if these hold, then G also holds. So, we are trying to deduce the validity of this thing, right. So, now if we take the negation of this, then we will look for satisfiability. So, if we take the negation of this, remember that this is going to look like not of f1 and f2 and dot dot fk or G, this and this are the same, right. So, if you take the negation of this, what are we going to have? So, if this whole thing is what we want to prove, so not of var phi is going to be f1 and f2 fk and not of G, right. And if this is valid, if var phi is valid, then not of var phi is unsatisfiable, right, then this is unsatisfiable. Now, is that clear? This is valid implies this is unsatisfiable. Clear? So, now this gives us a nice way of systematically doing the deduction. What we are going to do is, we are going to have a knowledge base, which is going to contain all these F1, F2, etc. through Fk. These are the things that are going to be present in this knowledge base. These are the things which are given to us. These are the facts and the rules, everything expressed in terms of Boolean formulas given to us, right. Now, you have given me a goal and you ask that is this goal implied from this knowledge base, can I deduce this goal from the knowledge base. So, what I am going to do is, I am going to push not of g into this and check whether this thing becomes unsatisfiable. So, I am going to push not of g into this, I will push not g into this and try to see whether I can prove that then this thing will become inconsistent or unsatisfiable, right. And how can I do this? See, we have all of these in conjunctions. So, if from any of these by any combination you are able to deduce false, then false ANDed with all of this is going to make everything false. So, what we will try to do basically, essentially what we are trying to do is, we are pushing not g in and trying to arrive at a contradiction. We are trying to take facts and rules and try to deduce a contradiction which will lead us to false, and the moment that we get false, we have shown that not g along with this is going to become unsatisfiable, and therefore, by this reasoning that we had shown here, g can be deduced from the set of facts. If this becomes unsatisfiable, then this is valid. So, g can be deduced from this. Clear? Right? Now, in case of propositional logic, it is both ways. If you find that if you are not able to derive false from this, that means that this thing is satisfiable. If this is satisfiable, then the negation of this cannot be valid, right. Now, what we have seen so far is that we can maintain a consistent knowledge base, and whenever we want to deduce something, we can push the negation of that goal in and then just call a SAT solver. Now, there are many very good SAT solvers that are available, which takes a Boolean formula and deduces whether the formula is satisfiable or not. So, you can now create you can have a SAT solver and you can create a complete reasoning system which will act as the front end. In that front end, you will be able to key in all your rules and facts, then you push the goal in, you translate this whole thing into a Boolean formula, feed it to the SAT solver at the back end. If it says unsatisfiable, then you say yes, your goal has been deduced. If it says satisfiable, then you say that the goal has not been deduced, right. Okay. But all this is based on what we call is monotonic reasoning. So, you have to ensure that at no point of time your the truth of your propositions change. Later on we will see cases of non-monotonic reasoning, where the truth of these propositions can change with new facts being introduced, right. So, that is going to make things more complex. We are not going to look at that right now. So, now to some results. So, in general, the inference problem is NP complete, Cook's theorem, we have all studied that in algorithms, is not it? Yes or no? Huh? Okay. So, you are familiar with what is NP complete? If not, then please brush it up. So, Boolean satisfiability is an NP complete problem. So, but in some cases we can have polynomial time procedures for doing the deduction. So, if we restrict ourselves to Horn sentences, where Horn sentences are of the form like this, then we can use modus ponens repeatedly to give us a polynomial time procedure. Now, what is missing here? There are two things that we are not allowing in Horn sentences. One of them is we are not allowing ORs here and we are not allowing ORs here. No ORs in the left hand side, no ORs in the right hand side, right. It is the ORs that will create problems. Now, this is just think of this as an exercise to find out that why is it the case that when we have Horn sentences, it makes life easier for us vis-a-vis when we have sentences where you can have ORs also on the left hand side. If I also allowed P1 or P2 implies Q, then it suddenly becomes difficult. Why so?
Elimination of an OR is much more difficult than eliminating an AND rule. With OR we don't have a clear way to eliminate. We assume something and then we eliminate, assume another thing, then we eliminate.
Yes, so you will not be able to directly use modus ponens to give you a definite answer to whether something is true or false. For example, if you had this thing implies Q or R, if you had something like this thing implies Q or R here, then when you have this thing in your knowledge base, you still do not know whether Q is there or R is there, right. So, intuitively that is what brings in the problem, but note that it is not the case that this thing does not have OR at all in the Boolean sense, because if you represent this in the implication, if you eliminate the implication, then this is going to be not of all these or Q. So, OR is there, but it is there in such a way that it is you can still use modus ponens repeatedly to derive new things. Now, there are two ways of broadly of doing this. One is that we start from the set of facts and rules that we have. We start from the set of facts that and rules that we have, and suppose that all these rules are given to us in the form of modus ponens. So, we can see whether the left hand side is satisfied by the knowledge base, and if so, then the right hand side is deduced in the modus ponens. If in an implication the left hand side is satisfied by the knowledge base, then the right hand side is can be deduced. So, you add the right hand side to the knowledge base, and then now check whether any of the other rules can be applied, right. If a new rule now becomes applicable, then again deduce the right hand side of that, put it into the fact base and keep on doing this until at some point of time you have reached the goal, right. So, this is called forward chaining. This is called forward chaining, where I am starting from the existing set of rules and I am trying to move forward. So, what I am not trying to explicitly deduce the goal. So, I have my all my implicational rules, right. So, which says A1 implies A2 and A3 implies A4 and so on, and A1 A5 A4 implies A7 and so on, and then I am just using these to deduce newer and newer facts and putting it in the knowledge base, and I am not looking that I want to deduce, let us say A9 and A11. I am not starting from this and working backwards, I am starting from these and working forward. So, it is forward chaining. The other option is to do backward chaining, where we start from A9 and A11 and then examine the rules and see which of the rules has A9 and A11 on the right side? Which are the rules that can give us A9 and A11 on the right side? So, let us say that we find that there is a rule which says A5 A3 gives me A9 and A7 and A9 gives me A11, right. Now, here we try to see whether any of these are being implied by this. So, we find that yes, A9 is coming from here, right. So, now by backward chaining I can replace this goal, I can replace this goal by A7 and A5 and A3, A5 and A3. So, my new goal becomes A5, A3, A11. Then I look at A11, okay, I can get A11 if I have A7, A9, right. So, I replace A11 by A7, A9. Then again I can apply this rule to eliminate A9 and I have A5, A3, right. So, I can eliminate this. Now, see, this is an extra step that I had to do. If I had actually in the initial configuration when I had A9, A11, if I had applied this one first, then this would have got reduced to A7 and A9 is already there, and then by another application of this rule I would have got A7, A5, A3, right. And then we go on backwards like this until we arrive at the set of facts that are there in the knowledge base. And when we have the set of facts in the knowledge base, then we say that that is solved, right. Now, do you see some similarity of what is happening here with problem reduction search? This is what we have to get. So, this is actually an AND of A7, A5, A3. So, I have to get A7, I have to get A5, I have to get A3. In order to get A7, some rule might tell me that you might have two rules for A7. So, suppose I have to get A7, A5, A3. So, this is an AND of A7, A5, A3 that I have to get. And then there are two rules, one which says that A2 and A3 gives me A7 and another rule which says that A4 and A15 gives me A7. Now, here I have an OR node, one for this, one for this. If I am here, then I have to, if I choose this rule, then I will have to solve A2, A3. If I choose this rule, then I will have to solve A4, A15. What do I mean by solve? I have to see whether these can be deduced from the knowledge base. So, again this is an AND of A2 and A3 and this is an AND of A4 and A15, and this is actually a graph because you see this A3 and this A3 are the same node, right. And then again we see what rules can give us A3. We go backwards until we hit upon the set of basic facts that are given to us. Suppose it is given to us that A4 is a fact, A4 is always true. That means that this is a node which is solved, right. Okay. So, we now have, as discussed, we have two strategies. One is forward chaining, where we start from the beginning and start generating new facts and rules, new facts rather, and putting it in knowledge base and keep on applying the set of rules. And we have backward chaining, which does the thing from the goal backwards, right. Now, try to think of the scenarios where forward chaining will be useful and where backward chaining will be useful. There are deduction systems which employ forward chaining, there are also deduction systems which apply backward chaining. think in terms of the branching that is there and also the depth of the deduction that you may have to do. Yes. So again the actual search. So you see this deduction is actually, it involves search. It involves searching in this rule space to determine which rules to apply in what sequence to be able to derive the thing, right. So we are going to we are not going to explicitly go into the exact search procedures for deduction, because you already now have some background on search. So you can figure out that what kind of search will be able, you will be able to do deduction with. But interestingly, there are actually platforms for programming where this kind of backward chaining is built in. So you have studied programming languages like C++, etc., which are procedural programming languages. In this course we will study a language called Prolog, which is a logic programming language. In this logic programming language, you are just specifying your facts and rules in the form that we mentioned, in implicational form, right, and this mechanism of backward chaining is built into the interpreter of the language. So you will see that computation will be viewed in an entirely different perspective when you talk about logic programming, and from a programming point of view it is very interesting to see how to take a program which you would normally implement in procedural language and see how you can solve that in logic programming. So it is not the case that logic programming is going to give you any additional computational advantage, it is only the representational advantage. You can write the program for 8 queens in 5 lines, you can write the program for TSP in 5-6 lines, that is where the advantage lies. You can write it in a very crisp form, and this mechanism of computation in backward chaining is built into the interpreter. So when we study Prolog, we will go into that. So we conclude this lecture here. We will start off in the next lecture on first order logic. That is where we will talk about quantification and see what are the advantages there. In the last class we had seen we had studied propositional logic, and we had seen some basic ways of doing reasoning with propositional logic. So today we will extend the logic further and move onwards to what is called first order logic. So in first order logic, the main, so what we have done so far is we have seen how to represent a problem in logic, we have seen propositional logic, we will now see first order logic, and then we will finally study how we can do inference in first order logic. Right. So the difference between first order logic and propositional logic is in the existence of predicates. Now if you recollect that in propositional logic we had propositions which could take values of either 0 or 1. So anything that we want to represent is in terms of propositions which have a Boolean value, true or false, right. Now unlike that, in first order logic what we are going to have is, we will have things called predicates, and predicates can have one or more arguments. So you can have a predicate which has arguments x, y and z, right. Now there is no truth value that we associate with this predicate as such, but we can always say that for all x, for all y, for all z, I have p x y z. So then this whole thing has a truth value. So this whole thing can be true or false. So if it is the case that for all values that x can take, for all values y can take, for all values z can take, this is true, then this whole thing is true. In other words, when these are like variables, x, y, z are variables. So, if you assign some value to them, now these values need not be numerical, it is some instantiation that we do to these variables. We assign them some value from the domain of these variables, and if we know, or if the knowledge base already contains the fact that for those variables this predicate is true, right, then we say that for that value, for that value of x, for that value of y, and for that value of z, p x y z is true, right. Similarly, you can have there exists x for all y, there exists z, p x y z. That means that there exists some value of x such that no matter how you pick your y, there will always be some z which is able to satisfy p x y z. P x y z has a truth value when x, y, and z are instantiated to some values, right. So, P of Tom, Dick, and Mary can have a truth value, right. But if you just leave them as person x, y, z without instantiating them to any value, then we cannot say whether that is true or not, right. But we can have these quantifiers, and we have two types of quantifiers, namely there exists and for all. I think you are familiar with these things from discrete structures. So, this means that there exists some value of x for all, such that for all values of y there exists some value of z which satisfies p x y z, and it is not difficult to see that the positions of these for alls and there exists y's are, they are not commutative. So, this is not the same as writing for all y there exists x, there exists z, p x y z. Though it may be cases where one implies the other, but these two are certainly not equivalent, right. So, we cannot actually move the quantifiers across each other, they will have different meanings, and we will shortly describe a set of things that we can do and we cannot do on this kind of logic.